Alright, I'm going to work through the 2024 Geometry Final Exam. I don't want to edit this, so you may have pauses while I think about things, and that's that. I'll try to break this into chapters in the final video so that you can skip directly to, not chapters, but numbers, so you can skip directly to a number that you need help with. Calculate the value of each interior angle of this regular heptagon, 7-sided polygon, and then use the exterior angle conjecture to calculate the interior angle to confirm that it's the same. Show your work. So we've got 7 sides, 5, 6, 7, and that means that this can be broken into 5 triangles, 1, 2, 3, 4, 5, each with 180 degrees. So 5 times 180 degrees should give us the entire set of interior angles. By formula, that would have been n minus 2 times 180, so it works out. 5 times 180 degrees will give us all of the interior angles, but we want just a single one, so we'll divide that by the number of interior angles, which is the same as the number of sides, or 7. So 5 times 180 is really twice 360, and then one more 180. But I can do it out longhand, and should get the same thing. So 900, is that twice 360, which is 720, plus another 180? Yes, it looks like that's right. Okay, so 900 degrees by 2 different ways. 900 degrees is the entirety of it. I have to divide 900 degrees by 7. I'm going to do this upside down. 7 into 9 is 1. So that leaves us with 2. It's almost 3. 14 would give us 6. Left over 60. 7 times 8 is 56. So that's a remainder of 4/7. So if I were to round up, this would be about 129 degrees. So anything in the range of 128 point something, rounded up to 129 degrees, should work. All right, exterior angle conjecture reminds us that each of these exterior angles extending a line forward is the same if this is a regular heptagon, and that adding them all up creates a full turn. Like if I was facing this direction, then if I went all the way around, I'd be facing this direction again, and that's 360 degree total around the entire thing. So I need to divide the 360 degree total by 7 sides. So 7 into 360 is 5, it's 35, 10, 1, something. So we have about 51 degrees rounded down. And 51 degrees here plus 180 degrees here is going to give us 231 degrees. 231 degrees would be this entire outside. So what's the inside right here? Well, it's 360 minus 231. I'm just going to round it for now. It's 230, so that's going to give me 3. So 130 plus 230 is 360. So something like 129 or 130 degrees. Sure enough, that does coincide well. And so the two different approaches give us the exact same interior angle for each angle of this heptagon. Number 2, a shape is made of coordinates 0, 0, 12, 5, and 5, 21. What's the slope of the bottom edge of this shape? Now, many of you used graph paper to get these precisely positioned. I'm not going to do that. I'm going to give myself a general idea. 0, 0, 12, 5 means out 12 and up 5. 5, 21 means out 5 and up quite far, 21. So it's going to be a shape that looks, a triangle that looks approximately like that. And that's good enough for me. I'll go ahead and label these as 12, 5, and 521 to help me know my orientation, but really what I've got here are slopes which are just the rises, the amount you go up over run, the amount you go over. So the slope of this line is this rise distance from the 0, 0 line, from the 0, the abscissa itself, up to this y, which is 5. So that rise is really just a rise of 5. And this run from 0, 0 to this point, 12, is really just 12. So I've got 5 over 12 as my slope here. 5 over 12. That's the slope, or m, of the bottom edge. It says, what is the slope of the bottom edge of this shape? It should be 5/12. Calculate 2 points that define the shape's mid-segment that is parallel to the bottom edge. So mid-segments are these halfway points that are parallel to the bottom edge. So I should have this guy right here, mid-segment, should be the same angle, the same slope as the bottom edge that we just calculated, and the 2 points, the endpoints of that should be halfway up this line and halfway up this line, right? And so again, my job is relatively easy even without graph paper. I just know that going upwards to this high point of 21, all the way up to 21, well, to get to the halfway height of that, I just need to go half of 21, or 21 halves, and that should be 10.5, right? So this right here should be 10.5. That's the y value of that guy. And the x value is going this direction. Well, I have to get halfway to 5, right? 5 is the x value of this point. So halfway to 5 is just 2.5, right? This should be 2.5. So this point right here should be 2.5, comma, 10.5. So I've got my slope, I've got my mid-segment, left point is going to be 2.5, comma, 10.5. That's that one right there. This one right here is similarly going to be halfway between this point and this point, both vertically halfway between them and horizontally halfway between them. So horizontally halfway between them, we're going from 5 to 12. 5 to 12. The difference between 5 and 12 is 7. So I need to go half of 7, or 7 halves. So I'll write this one as 7 halves, although we have to add that to our 5, right? So this right here, this distance from here to here is 7 halves. But I already went 5 from my y-axis, so it's actually 5 plus 7 halves. That's the horizontal. We're going to do the vertical in just a minute, but this can be basically 10 halves plus 7 halves, which is 17 halves. And if you want to write that in an improper fraction, well, 16 halves is 8, so it's 8.5. All right, so that's our x value. How about our y value? Our y value again is the distance here between this point and this point in half. Well, it's 21 high here, and it's 5 high here. The difference between 21 and 5 is 16, right? So we've got 16, a rise of 16 from here to here. Half of that is 8. So we've got 8, but we have to add that 8, that rise of 8, to the original starting point. So we go up 5 to get to this point, and then up 8 more to get to this point, and so it's 5 plus 8, and that's 12. So our y value here is 12, and our midpoint, okay, I have a correction for number 2 here. Added 5 plus 8, and got 12. Obviously that's 13, so the mid-segment's right point should be 8.5, 13. Is this point right here, 8.5, comma 12. Our left point was 2.5, comma 10. Box the whole thing there, and so our full answer is that the slope is 5/12. That's the slope of this line. The midpoint, mid-segment left point is 2.5, comma 10.5, and the mid-segment on the right is 8.5, comma 12. If I were to do a slope, a rise over run calculation with this rise and this run difference, I should also get 5/12 as my slope between those. Number 3. A Mesopotamian ziggurat, when viewed from the front, is a rectangular trapezoid with bases 64 meters on the bottom and 55 meters on the top. So I want to make a regular trapezoid with a 64 meter base on bottom and a 55 meter base on top. I haven't done a very good job of making that look regular or symmetrical, but you can use your imagination. It's got a height of 26 meters. So this height right here is 26 meters. And a perimeter measurement of 179 meters. So the perimeter all the way around is 179 meters. What is each sloping side length? So I'll call that x. What is x? What is the area of the trapezoid, the base angles, what are the top angles, and finally what is the mid-segment length, halfway up from the ground? All right, let's start with the sloping side length. We've got a perimeter of 179 and a height of 26. We're going to need some elements related to the area. If we remember the trapezoid area formula, great. I'm actually going to go back a little bit further and say I don't remember the trapezoid area, so I want to think a little bit about breaking my trapezoid up into parts. I've got a triangle over here and a triangle over here, so together those two are going to make a rectangle. It's 26 meters tall. If I flip this and put it right here, for instance, I'll have the other half of the rectangle here. It's 26 meters tall by some amount here. Well, we have a 55 meter length from here to here. That means that the remaining distance is split up between these two. 55 to 64 is 9. So 4.5 meters on this side, 4.5 meters on this side, and we have a rectangle here of 4.5 meters by 26. 4.5 times 26 is the area of these two shaded regions together, triangles. And then we're going to add the area of this midsection, which is just a rectangle that's 55 by 26. So I'll add 55 by 26. All right, this is some math that I'm tempted to use a calculator on, but I think I'll just go for it. We'll just do this long math-wise. I'm going to put the 55 on bottom so that I make my life easier. 3, 10, and 13. So the other one's also going to be 13 or 130. 0 there. I've got 1430 on this side. 26 times 4.5. That one I don't see any obvious cheats, and so I just have to do the 130 again for that one. And then 4 times 6 is 24. Add 2, 8, 10, and we have 7, 1170. I've got to remember I have a single decimal point here, so I've got to move my decimal point in. I have 117 plus 1430. 117, 7, 4, 5, 1. So about 1547 meters squared is my overall area. And that's going to answer this second question here. What is the area of this trapezoid? What about these sloping lengths, though? How can we get the sloping lengths? Well, it turns out that I went ahead of myself. I didn't really need this area for the sloping lengths, did I? Because we have the fact that the perimeter is 179 meters, and the perimeter is just the sum of all the sides, which is 64 plus our sloping length x, plus, so that's from here up to here, plus the 55 meter top, plus our sloping length x again. You can combine the two x's and I get 64 plus 55 plus 2x is 179. This sum, 64 and 55, are 9 and 11. And so I have 119 plus 2x is equal to 179. If I subtract 119 from both sides, I should get a nice round number here of 60. and that's 2x, and if I divide both sides by 2, I get myself an x of 30. So 30 meters is my sloping side length, and this is my area. And I've answered 2 of the 4 questions here. Sloping side length, area of the trapezoid, which is called the ziggurat's cross-sectional area. So yes, this is a 3D shape. You know, presumably you could look at it a number of ways, but this would be like I sliced right down the middle of it, and that's the cross-sectional area. The base angles of this trapezoid shape are 87 degrees. So that's here. I'm going to redraw this briefly. Maybe I'll do a better job. So we have an 87 degree base angle there. And what are the 2 top angles? So if these 2 are 87, it is regular, then we should get 360 total out of those 2 87 degree angles plus these 2 angles, which I'll call alpha and alpha. So plus 2 times alpha. 2 times 87, well, that's 14, 16, 17, 174. So 174 plus 2 alpha is 360. I'm going to subtract 174 from both sides. We get 6, 5, and 1, 2, 3. Let's see, I'm going to double check myself on this. It doesn't feel right. 7 plus 6 is 13. Oh, I didn't get anywhere close. This is actually 3. Sorry. 3, 4, 5, 6, and 2, 3. So 213 degrees equals 2 alpha. I have a correction for number 3. Here, this subtraction of 174 got swapped around to be 147, so this would come out differently, and the end result would tally to 93, not 106 and a half. Arithmetic error. Doesn't divide by 2 very nicely, but that's okay. We can do it. I'm going to go ahead and do this as a division, upside down division again. 2 into 2 is 1, 2 into 1 is 0, 2 into 13 is 5, or 6. That would give us 12 with a remainder of 1. So 106 and a half should be our alpha, 106.5. Okay, that is, oh, I'm sorry. And yes, that's right. So that is one angle, right? One of these angles up here, 106.5 each. Okay, finally, what is the mid-segment length halfway up from the ground? So we have these original lengths of 64 and 55. The mid-segment has to be halfway between those two. There's 2 ways to do that halfway problem. One of them is to say, well, a halfway between, or a midway or a mean of many numbers is just the average of those numbers. So I could do 64 plus 55 and divide by 2. Or I could find the difference between 64 and 55, so 64 minus 55, and divide that by 2 and then add it to 55. I'm just going to go ahead and do the standard averaging technique of 64 plus 55, which is 9 and 11. And I'm going to divide that by 2. So 119 over 2. Well, that's going to be another division. 2 into 10 is 5. 19. 2 into 19 is 9, which is 18. And then I have a half, so 59.5 left. So 59.5 is the length in meters of the mid-segment. Mid-seg length. Just as a quick sanity check, 59.5 should be more than 55, and it is, and less than 64, and it should feel about halfway in between them. If you wanted to double check again, you could do a subtraction to get the difference, divide that by 2, and then add it to 55, and it should also give you 59.5. All right, that's number 3. Number 4, construct a rhombus, ABCD, with AC, notice that A and C are across from one another, equal to X, and BD equal to Y. All right. All right, so this is the length x that we're concerned with, and this is the length y that we're concerned with. So I'm going to go ahead and open up my compass to the x length to give me my my distance from A to C, and that's going to be my short distance. I'm going to go ahead and just do a sweep right there, and I have my point right here. So I can go ahead and make a line. I'm going to have to assemble myself a straight edge here, having failed to prepare to bring one. And so I'm going to go ahead and say that this right here is my AC. We'll call this C and this A. That is my AC, which is a distance of x across from one another. My rhombus is going to be some tallness, so I need to actually create a perpendicular bisector of AC. That's going to require some distance a little bigger than the halfway point, and I'll do that, and I'll do this, and I got very close to perpendicular there. This right here will be my the line on which my BD falls. I have to still cut this in half somehow. So I need to take my y distance itself and cut it in half. This is a big one. I'm going to open this way up here. And so there we are. That's y. So I can again just go ahead and make myself a y for the purpose of finding this halfway mark. So I'm going to pull my compass in a little ways, give myself a sweep, and give myself another sweep. Oops, I didn't give myself very much there. I'm going to do it again. That doesn't feel like quite enough material to make a nice straight line in. So here's my outer circle, and here's another outer circle, and that gives me plenty of distance. For accuracy, I've got a point there and a point right here. I'm going to connect those 2 points, and that's a nice perpendicular bisector, which means that if this whole thing is of length y, then half of y is the distance of half of that, which is where my bisector landed, right there. So that is half of y. Now I can put my point on that mid point and give myself crosshairs above and below. It shows me that I did not quite draw this line long enough. So here I have a B and a D, so that BD is equal to y, and half of it is perfectly in the middle. If I simply took y and placed it random in here, it could be that my rhombus was more of a kite than a rhombus. But as I've done it here, this should come out to a perfect rhombus where all 4 sides are equal. And that's number 4. All right, number 5. I'll do it this way to keep things nice and clean. Draw the perfect path to sink the white ball into the black hole. There's room on the page below to complete your construction to create this path. This is a top-down view of a mini golf hole, so you're in the air looking down at it, and that's water in the middle, so we cannot simply sink the white ball into the black hole by going over the water. You must go around it, so we have to think about a path that could go around it. It can't go around in this direction at all, and if you want to try to go around this direction, you'd have a hard time getting it to bounce and not just land in the water, so we're pretty much going to have to go to this wall, then to that wall, then to that wall, and then to that wall, somehow like that. Now, we don't have to know exactly where these points are yet. We just have to know that this is wall number 1 that we're going to reflect across. This one is wall number 2 that we'll reflect across. And finally, this is wall number 3 that we'll reflect across. So reflecting across wall number 1 means creating ourselves a mirror image on this side for the ball to see. And so how do we do that? Well, we're going to go ahead and position our compass so that we can give ourselves, just open it up a little bit more so I don't interfere with myself, and close it a little more. Okay, so I'm going to give myself a couple of hash marks, one on this side. It's a little bit too big. There we go. So a hash mark here and a hash mark here. I was afraid of hit my number there. So right here and right here, those are those two. And if I leave my compass the same size, then I should be able to find a crossover on the other side here. And that right there should be the location of an exact image or reflection of the ball across that line right there. So hash, hash, and then hash, hash. Okay, so we have our reflection. At this point, we need to reflect this reflection across the second wall that we need to reflect across. So it'll be handy to extend this wall's line into space, and we need to extend that ball image up to here somewhere. So let's similarly create ourselves a couple of hash marks. I'm going to try to stay on the paper here. If I had made my ball very, very tiny, I could get this to locate very precisely right on that dot, and I kind of made my ball big, so I'm just going to try to aim for the center of it. I'm going to give myself a hash mark and a hash mark, and then I'm going to use the same size so that I have equal lengths. You know, each time I'm doing this, I'm basically creating a rhombus, right? This is a rhombus that I just created right here, because those are all equal distances, and perpendicular in the crossover right here. So those two crossed over right there. So I'm going to make a pretty small dot this time right in the middle of that. You see my estimate was off a little bit. So this would be reflection point number 2 across this wall. Now we need to reflect across the third wall. So I'm going to extend my third wall line up like so. And I need to reflect that across that wall. So I actually need this line to be just a little bit bigger so I can give myself a hash mark up high on my page. Okay, that should do the trick. So I have to open this up more than the halfway there, like so. And I'm going to give myself a hash. Of course, I intersected some of my writing yet again. So right there, and then I'm going to right there. I'm going to try to find this crossing. There it is. Right there, and it looks like my crossing point is right there. So now I have all 3 reflections, and I simply have to do some connecting of the dots. So I'm going to connect the dots from the white ball to the last reflection there, and that means that I need to aim this ball in exactly this angle in order to hit the wall right there. And then it will bounce perfectly because this distance right here is the same as this distance right here. This is an equilateral, or excuse me, an isosceles triangle right here. That will be the direction that the ball will go from that bouncing point, that first bounce point, to this wall. And then it'll bounce on this wall right there. And which direction will it go? Well, because this right here is an isosceles triangle, it'll go towards this reflection. So I'll connect these 2 dots. And finally, that bounces off of this wall and goes directly to the black hole. So that this angle should be the same as that angle. This angle should be the same as that angle. And this angle should be the same as that angle. Okay, And so we have reflection, 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 and sink. That's number 5. Number 6 is a true or false. The two transformations in which the orientation, the order of points that you move as you move clockwise or counterclockwise, does not change our translation and rotation. Is that true or false? So let's think through all of our transformations. There is a translation, there is a rotation. Those are the two that are being proposed that do not change the orientation of a shape. So that if I had a shape like this, and it had points A, B, C, D, and E, the sequence A, B, C, D, E would not change if I simply rotated this so that A was further around. You would still have A, B, C, D, E, nor would it change if I simply slid it somewhere. But what are my other transformations? So that seems true. It seems like translation and rotation do not change the order of those. But what are our other transformations? Well, one of them is reflection, right? And if we reflected this, then what would happen is reading this in this direction, A, B, C, D, would turn into reading in this direction, right? So our shape would be reflected so that E to A would be going in the counterclockwise direction instead of in the clockwise direction, right? Because we'd flip it over there. And so it's true that a reflection is not going to qualify as a transformation that keeps the orientation. And so it's good that reflection was not included here. Are there any other transformations besides translation, rotation, and reflection? Not primitive transformations that we've studied, so this one's going to be true. It's good. Number 7, a translation by -3, 7. In other words, 3 to the left and then 7 upward, followed by a translation, another translation, but this time 8, 12, meaning to the right by 8, quite a bit more than you went to the left, which was only -3, and then up 12, is equivalent to a single translation by 5, 5. So the idea here is that, is it true that if we go -3 and then +8, that we actually went +5? Well, yes, 8 minus 3, or -3 plus 8, does equal 5. So that's good. How about ascending 7, and then later on ascending 12? 12 plus 7 is 19. Aha. So since this is a +7 and a +12, we end up going up 19. 5, is not going to work because this should have been a 19 if indeed it was the composite translation composed of both of these. Now 5 is funny. You might think, well, 7 plus 5 is 12. So if only this had been -3, -7, where you went to over 3 and then down 7, and then over 8 and up 12, then you would get a 5, 5 out of it. So the fact that this was a +7 means that our answer here is false. But if it had been a -7, then our answer would have been true. So it was slightly tricky in that way. Number 8, true or false? A shape is reflected across a line, and then it's reflected across a parallel line that is 16 inches from the first line. So you have some shape. It's reflected across a line so that you have the shape again on the other side of the line. And then it's reflected across a parallel line that is 16 inches from the first line. Now this might seem funny. You might say, well, is it 16 inches this way? Or 16 inches this way? Those are two parallel lines that are 16 inches away. But this is the original shape. This is the reflected shape. If you now reflect this reflected shape across that line up here, you get an R2 up there. If you reflect it across this line right here, you'd get an R2 down here. Okay, so it's one or the other. And it says a shape is reflected across a line, then reflected across a parallel line 16 inches from the first. The shape is now 36 inches from its original position. Well, either it went some number of inches and then some number more of inches to get to R2, or it went some number and then went back again this amount. And the question is this distance right here the same, regardless, and is it 36 inches? So, what you're not given is the information about the distance of the original shape from this first line. Let's just project the idea that that was something like 1,000 inches. If you reflected across a line that was 1,000 inches, and then another reflection that was across the line 16 inches from the 1,000, then you're on the order of 1,016 some odd inches away in this direction. Likewise, if you reflect across a line that is 2,016 inches, if you reflect across a line that is 1,000 inches away from the original, and then reflect back this direction across a line that's only 16 inches away, it'd be a little bit different. You'd actually be just getting closer. You wouldn't go way up here, but 16 inches would be a small amount compared to 1,000, and you'd be right there, but you'd still be close to 1,000 inches away. So 36 inches is really just pulled out of a hat. It is of no real value compared to anything because you weren't told about the first line's distance from the first object. And so this one is false, or maybe more appropriately we would call this one undetermined, right? We don't know. It's possible that you could choose a perfect situation where you'd get exactly 36 inches, but it's not clear that that's the case here. All right, good. Number 9. Using your compass and a straight edge, construct the point of rotation that would result in triangle XYZ rotating onto X prime, Y prime, Z prime. So you see that this X has to kind of rotate around to X prime, this Y has to rotate around to Y prime, and this Z has to rotate around to Z prime. You might sort of just imagine that this center point must be somewhere in here to get these rotations to kind of come around like that. And to do this problem, our formula is to take any couple of lines, such as X to X prime or Y to Y prime, that connect the dots between the original shape, between corresponding parts of the original shape. And you might think, well, that's enough. Isn't this the position? But it's not. What we have to do is perpendicularly bisect these. You can draw a Z as well, and you can see that these three lines don't have any special relationship with one another. They form a triangle, but they don't do anything else. When we perpendicularly bisect these lines, we'll see something very nice. We'll see a convergence on a point. And so let's do that. I want something a little over halfway between X and X prime here. So I'm going to open my compass to about there. Give myself a sweep and a sweep. And X prime, give myself a sweep and a sweep. I now have 2 points, this point right here, and this point right here. That will bisect X prime perpendicularly. And I won't have to do all 3 of these because we'll see a convergence in just 2 of them, but I might do all 3 just so we can see to prove that. So I'm going to stabilize my compass here. Choose a distance a little bit more than halfway between Y and Y prime. Give myself a sweep and a sweep, and a little same thing from Y prime, a sweep and a sweep. And I have 2 points again here and here. I will connect those 2. And you see that this line and this line converge at this point right here. Let's see if Z, the perpendicular bisector of Z to Z prime, does the same thing. I'm going to put my compass a little bit smaller here, and let's try that again. And we'll sweep, and and sweep, and then Z prime, I'm going to sweep and sweep. I think I got the right one there, didn't I? Oh no, I don't think I did. Let's see again. Let me try this all over again. So Z, we have a sweep and a sweep, there it is. and then z prime. Too many sweeps here. Z prime is sweep and sweep. Okay, so I found this was the intersecting of the two sweeps there, and this is the intersecting of the two sweeps there. I'm going to go ahead and connect those two dots. And you see that all three lines, this one, and this one, they all converge on that point right there. So that is my rotation point. I should be able to put my compass on that point and open it up to say X. And it should be true that if I get it on X here, it should also land on X prime. Good. And I should be able to close it down to Y, and that should go around to Y prime. And finally, I should be able to confirm that Z rotates around to Z prime. And so there we have it. Each of those points will rotate about this point and land on the corresponding coordinates for the other triangle. And that's number 9. All right, number 10. John walks to a position where the shadow of the top of his head coincides perfectly with the shadow of the top of a building. So, let's get a new piece of paper here. And we're going to try to draw John and a building and the sunshine. Now you might have wondered about what if the sunshine was over here. In that case, we wouldn't really have a good situation because the shadow of the top of his head, wouldn't really correspond with the shadow of the building, which would be on the other side of him. On this side, the sunshine shines so that it casts a shadow, and the shadow of the top of his head casts a shadow too. So in this case, I'd have to walk my John out a little bit more and put his head, or grow him or something, put his head in line with the shadow so that the building top shadow and his head shadow correspond. He sees sort of this shadow of himself on the street and a shadow of the building on the street, right? The two correspond right at that point. Okay, so the building is 240 feet from him. This is 240 feet right there. And he is 6 feet tall, so this is 6 feet right here. Okay. His shadow is 12 feet long, so this is 12 feet right there. From where he stands to the top of his head shadow, okay? How tall is the building? What we want to know is, what is this? X. All right, so we have two triangles. This triangle right here, which is a 6 and a 12, and this big triangle right here, which is 12 and 240 combined, so 12 plus 240, and then X, an unknown height, and these two are similar, right? So that the 12 of this triangle corresponds to the 12 plus 240 of that triangle. 12 here corresponds to 12 plus 240, in the same way that the 6 of this triangle, his height, corresponds to the X of this triangle, the building's height. 6 corresponds to X. So now we have a cross multiply and divide, or a straight up algebra. We'll go ahead and do the cross multiplies. The 12 times X should be the same as the 6 times 12 plus 240. That's 252 times 6. 252 times 6, 6, 12, 31, and 13. We have 13, 12 equals 12x. Here I have a correction for number 10. The division, the subtraction here, or multiplication here would result in a carrying of 3. 6 times 5 is 30, or plus 1, so 31. 3 added in would make this 15. The division would come out to 126 feet, not 109 feet. So let's divide both sides by 12. I'm going to do this one very funny. I'm going to divide, no, I won't do that to you. Let's go ahead and put our equal sign over far enough that I can put 12 in right here and divide this by 12 upside down. 12 into 13 goes once. 12 into, and these are a remainder of 1. 12 into 11 goes no times, but 12 into 112 should go about 9 times. Often a 0 is followed by a 9 when it's close. So 12 times 10 would be 120. So 9 is indeed less than that. It's 108. And that leaves us 4, or 4/12. Okay, number 11. Two triangles have vertices. Triangle 1's vertices are given here. Triangles 2 vertices are given there. Are the two triangles similar? All right. So again, this one you could do on a piece of graph paper. I'm just going to give myself a rough indication of what these two triangles look like. We've got our origin of 0, 0. Make this a little bit bigger for you here. So we have our origin of 0, 0. So we've got a triangle with 3, -4. That's going to be down here. 3, 6. That's going to be up here. And 12, 6. That's going to be here. Notice that this has to be a right angle because these two x values, 3 and 3, they're both 3 in. So this has to be a vertical angle, a vertical line. And these two values, y values, are 6 and 6. So they're both 6 up from the base. And so this has to be a horizontal line. That might become interesting. Triangle 2 has a value of 3, 1, which is right there. 3, 6, which is the exact same dot as that one. And 8, 6. So that's going to be right in here. It's okay. Yeah, it's okay. I'll be finished with this one in a minute. And so they almost look like they're already similar. We have two vertical lines, two horizontal lines. That's kind of nice. We just need to know if these two lines are parallel. And if they are, then all is well. We could do it in any number of other ways as well, like taking the ratio of this side length to this side length, and this side length to this side length, or whatever. As well, but I think I'm going to take the approach of wondering about this rise over run. So this is 6 high, and it came from 4 down, so this is basically a 10 rise right there. And what is our run? We go from 3 over to 12. 3 to 12 is a difference of 9, so we have basically a 10/9 rise over run. Slope of 10/9 there, and let's see if the same holds for this guy right in here. So he's at 3, 6, and I'm sorry, 3, 1. This is our 3, 1. Just a second. And this point right here was our 3, 6. So our run here, no, I'm sorry, this was 8, 6. So our rise here is from 3 to 8. And that's a 5 height. And our run is from 1 to 6. That's a 5. Oops, that's a 5 height. So that one is 5 to 5, or a slope of 1. It's not the same. It's very close to 10/9, but not the same, so we have to say no. They're not similar. That's 11. Okay, on to number 12. Number 12 says, what is the area of a triangle with a base of 12 and a perpendicular height of 6 meters? So this one's fairly straightforward. The base of 12 and the height of 6. Only requirement is that you remember that the area of a triangle is 1/2 base times height. So we have 1/2 6 times 12. Half of 6 is 3. 3 times 12 is 36. So our area is 36 meters squared. Number 13. What is the area of a trapezoid with bases 13 and 7? 13 and 7. And this is actually doesn't say that it's a regular trapezoid, and it doesn't really matter in this case. So these slants could be different. But we have a height of 9 inches. Now you can either do this problem from the formula, using the idea of the average of these two bases, 7 and 13, to essentially convert this into a rectangle. And that would basically look like 13 plus 7 over 2, or 20 over 2, which is 10. So this is equivalent to a rectangle with base 10 and height 9, which is a 10 by 9 or 90 square inch area. Or you could have broken this up into triangles, though you would have to think a little bit about how they fit, since this isn't guaranteed to be regular. All right, number 14. You need enough dye to dye 100 kite-shaped kites. The kite diagonals are 24 and 36 inches. And so we'll have our kite, looks like this, and our diagonals of 24 inches and 36 inches. Each pint of dye covers 1,000 square inches. So 1 pint will cover 1,000 square inches, SQIN. How many pints are needed to dye 100 kites? So some number of pints to dye 100 kites. So we need to know the area of the kite in order to get the square inches of dye. We're going to just assume here that the dye will dye this many square inches through the entire kite, but if you thought that you needed to dye both sides of the kite and therefore needed to double the surface area here to be dyed, then I'll give you full credit for that, because that's fine and clever. The area of this kite, of course, is just the area of a rectangle made by moving this triangle to there and moving this triangle to here. So in essence, we have a 24-inch by 36-inch rectangle out of this kite. And thus we have a 12-inch, which is half of the original 24 there, 12-inch by 36-inch rectangle. So it's very much like a triangle, 1/2, I guess, diagonal 1 times diagonal 2. So if we write it out like that, 1/2 of 24 times 36, that's 12 times 36, which is 72, 36, this is 13, 432 square inches. And that would be the, so in order to cover one kite, we would need about 1/2 of a pint, because this is 432 square inches, and a pint would cover 1,000 square inches, so that should give us a general idea. Basically, we have that we want to cover 100 kites, and we know that 1,000 square inches, that 432 square inches per kite. So one kite has an area of 432 square inches. So this original setup here will get us to cancel kites. And then we also know that 1,000 square inches of dye will 1,000 square inches of a kite will be covered by 1 pint of dye, so that will cancel our square inches and should give us in the end just pints, which is what the question asked for. How many pints? Okay, so this is just a straightforward math here. 100 over 1,000, that just cancels to 10. So we have 432 divided by 10, which is 43.2 pints. Okay. Number 15 says, true or false? The area of a kite is half the area of a rectangle that circumscribes it. So again, we looked at this a little bit with 14, but if we have a kite that is A, tall, and B, width across, then the rectangle that would circumscribe it would also be B, width across, and would be A, tall. That rectangle there would be A times B. But of course, that's each of these is cut in half because it's a triangle. So this is half of the area, and this is half of the area. This is half, and this is half. Another way of thinking about it is that this triangle is congruent to that triangle, and so it can be moved into this space right here, and it fills that space. Likewise, this one can be moved into this space, and it fills that space. And so we have a rectangle right here that is still A tall, but it's only half of B wide because we got rid of everything on this side. So indeed, it's 1/2 times area, or it's 1/2 times A times B. It's 15. 16, true or false? The length and width of a rectangle are each doubled when the area of the rectangle is doubled. Okay, so in 16, if we want to double the length, let's call this the length and this the width. If we want to double the width, we're going to make this rectangle twice as wide or twice as tall as I have it here. And we're going to double the length, making it twice as long. As you can see, in doing so, we've basically created 4 rectangles where there was just one. So we're not actually doubling the area, we're quadrupling the area. Or in other words, we're taking the double side dimension and squaring it in order to get the new area dimension, because an area is always a squaring of some side, like side times side. It's a square. For a rectangle, you've got length times width. So anytime you change the scaling by some number, you're going to change the areas by that number squared, or 4 times. So it says, true or false, the length and the width are each doubled when the area is doubled. That's false, because it would have to be, quadrupled. When the area of the rectangle is quadrupled, then the length and the width would be doubled. This one was true, and that was here, number 15. So false on this, true on that. And we're on to number 17. Number 17. True or false? If the length of a mid-segment of a trapezoid is 30 meters and the height is 12, then we'll have a trapezoid here. And the length of the mid-segment is 30. That means that this shorter top, maybe it was 25 or so, would be shorter by the same amount that this longer bottom would be longer. Something like 25 and 35. This could be 24 and 36 or whatever. I'm sorry, 24 and 34, or 26 and 34 or something like that. So its height is 12 meters. Then the area of the trapezoid is less than that of a rectangle with a base of 6 and a height of 60. I didn't draw that very well. A base of 6 and a height of 60. That rectangle's area will be 60 times 6, or 360, right? So this area is 360 meters squared. This area, it turns out, is the same as a rectangle of 30 by 12, because it doesn't really matter what the two legs are as long as the average, which is the length of the mid-segment, is 30. It's just like a rectangle that's 30 by 12. 30 by 12 here is 6, 0, 30, that's 360 meters squared. So we have 360 meters squared, whether it is this trapezoid shape or this rectangular shape. So it says the area of the trapezoid is less than, well, no, they're the same, so this has to be false. They're the same, not less than, so this is false. Okay, number 18. True or false, if the area of a sector of a circle with radius 8 inches is 24 pi inches squared, then the central angle of that sector is 135 degrees. So we're looking for a sector, or a 135 3/60ths portion of a circle. This given circle has a radius of 8 inches, so its area, the area of a circle equals pi r squared, so its area is pi r squared, pi times 8 squared. And we're looking again for a sector that is 135 3/60ths of that area. So if we do this, math out, 24, 32, I'm going to do this carefully here. 8 squared is 64, so I'm going to write 135, 360, 64 pi. Take the pi and the 64 and swap them. 64 and 36, nope, 36 doubled is 72. I don't have an easy time of this, so I have to decide what to do first and second. I think I'll go ahead and just do it out straight. I'm going to do 135 times 64 and then divide by 360. I can't remember if I let you guys use calculators or not. Let's make sure that I'm going down the right path here. This should give me 24 pi. So I'm looking to see whether or not that is 24 pi. Or whether or not this math right here, 135 times 64 divided by 360, is 24. So a little bit laborious here and accident prone, but I'll give it my best shot. 2, 12, 14, 5, 0, 0, 3, 21, 2, 8, 8, 6, 4, 0, divided by 360. Not very easy. I'm going to say 2 with the idea that I'm hoping for 24 here. I can't do that upside down with the math, so I'm going to turn it right side up. 8, 6, 4, 0. I'm hoping for 2 here. 0, 6, 2, 6, 7, 4, 4, 1. That is less than 360, so we're on the right path. And then since I'm given 24, I'm going to give this a shot and see if it works. 4 times 0, 4 times 6, 24, 4 times 3, 12, 13, 14. And look at that, it comes out nicely. So this one did work out to 24, and so this one is true. Number 19. True or false? If a triangle is scaled up so that its sides are each 3 times the lengths of the original sides, then the area scales up by a factor of 6. All right, so I have a triangle. I'm going to make my life easy by thinking about it in terms of a right triangle. It's scaled up so that its sides are each 3 times the length of the original. I'm just going to give an example here. Let's do 2 and 3. If we scale this up 3 times, this now becomes 2, 4, 6, right? We're going to make a big triangle here. This would become 6, and this one would become 3, 6, 9, right? So that is 9. So this triangle is going to be one area, is going to be 1/2 9, 6, or 9 times 3, which is 27. The original one was 2 by 3, so the original triangle, A1, was 1/2 2 by 3, which was just 3. So you see we scaled up by a factor of 9 here. And this says the area scales up by a factor of 6. So it doesn't scale by 6. It scales just the way a square or a rectangle or a circle scale. If you scale a side or a one-dimensional measurement of the shape by something like 3, then you're going to have to square that, 3 squared, to get the scale of the area, so which is 9 in this case for my example. So by example or by analysis, you can come up with this, that this would really have to be 9 if we took a dimension and multiplied it by 3, because 3 squared would be 9. So this one's going to be false. Number 20. Write the area formulas for rectangle. We'll call that rectangle. Let's call it area of a rectangle, area of a triangle, area of a circle, and area of a kite, and an area of a trapezoid, and an area of a parallelogram. It wants us to give all of these. If we didn't know them by heart, we could work them out, I believe. So a rectangle is, of course, just length times width, or length times height, however you want to call that. That's just fine. Area of a triangle is 1/2 times the base times the height, or length times height, however you want to call that. The area of a circle is pi r squared. The area of a kite is going to be its diagonals, so diagonal 1 times diagonal 2, and 1/2 of that, just like with a triangle. Okay, you can call that 1/2 x times y, or 1/2 a times b, whatever you do. If it's something along these lines, you'll get credit for that. The area of a trapezoid requires, remember, that we turn this trapezoid in our heads into a rectangle, where the base is the average, or the middle between these, the short and the long. So if we have base 1, 1, and base 2, we'd be talking about base 1 plus base 2 over 2. That gives us our length, basically, for our rectangle. And it's that times the height to give us our area. So something of this form will do. And finally, the area of a parallelogram. A parallelogram like this is always going to give you the height, or you'll need to find the height somehow or another, and the base length, the length of either the top or the bottom, because they're the same in a parallelogram. So I'll call this just base times height. It doesn't matter that it's leaning over sideways. There's no difference in between this and a rectangle of the same dimensions, because of course this little missing triangle in a rectangle could simply be placed right here, and you would have a rectangle. Okay, those are all of the areas, and that's number 20. Number 21. The ratio of the perimeters of two similar parallelograms is 4 to 9. So we have a parallelogram here, and its area is, its perimeter. That's a one-dimensional argument. Its perimeter is 4 times something, and the perimeter of this bigger one is 9 times something. So there's a scale factor of 4/9 in essence, or 9/4, depending on how you look at it. 9/4 of this area would give you this, of this perimeter or side length would give you this perimeter or this side length. What is the ratio of their areas? Again, it's always true that the ratio of an area is going to be squared by comparison to the ratio of one-dimensional components like sides. So we're just going to simply square this, and we'll use, since they say 4 to 9, we'll use the 4 to 9 version. We need to square that, which would be 4 squared or 16, and 9 squared or 81. And so we have a 16 to 81, or 16 to 81 scale factor for area, the area of the small to the area of the large. Okay, number 22. Find the area of this parachute shape right here, which is 20 meters wide. That's 20 meters wide. In other words, each of these is 10 meters. and made up of 3 perfect semicircle shapes. So I couldn't have told you that this was 10 meters if it didn't tell me that they were perfect semicircle shapes. Now you know that they're 10 meters apiece. You can leave your answer in terms of pi. So we have the outer circle, or half of the outer circle, which is half of the area of the outer circle, or pi times radius. For the outer circle, the radius is 10 squared. Half of pi times 10 squared would give us the entire thing. And we need to subtract off an inner circle, or 2 halves. So 2 times half, which is really just 1 inner circle made up of these 2 halves, where the radius is only 5. So it's pi times 5 squared. These parentheses are unnecessary. It was just a way of suggesting that we're doubling and halving that whole thing. But since this is all multiplication, it can be done in sequence. Okay, so here we have, again, 2 times a half is just 1. So we have on this side of the subtraction pi 25. And on this side of the subtraction, we have 100 in half, which is 50. So we have pi times 50, or 50 pi minus 25 pi is going to give us just 25 pi in the end. 25 pi meters squared. So our area of the kite is 25 pi meters squared. Notice this is I'm sorry, I said kite. It's a parachute, not a kite. Number 23, we have, what is the arc length in inches of an arc whose radius is 7 and degree measure is 45? All right, so we have the radius of a circle, very well drawn there, but we're talking about just a portion of it that corresponds to a degree measure of 45. All right, haven't drawn it well, but that's the idea. So in other words, we're talking about a portion of a circle. I should really draw this better to kind of think in terms of what that means. If I start my circle here, a 45-degree angle in this direction is halfway to a 90-degree angle. A 90-degree angle would be 1/4 of a circle, right? 2, 3, 4 quarters of a circle. So a 45-degree angle is just halfway to a quarter, or this is we're talking about 1/8 of the circle. So if we knew our circle's full circumference, then we would just take 1/8 of that circumference, 1/8 of circumference, to get this arc length right there. So we have indeed a radius of 7. So our circumference, C, would be 2 pi r, or 7, and that's just 14 pi. And 1/8 of 14 pi, 1/8 of circumference is 1/8 of 14 pi. That goes 4, 7, so we have 7/4 pi. So that is the arc length, where we're given dimensions here, inches. So 7/4 pi inches is our arc length, number 23. 24, what is the radian measure of a 270-degree angle? So a 270-degree angle, there it is 270 of 360 degrees. That's the ratio, or the proportion of the degrees that we're concerned with here. We know that radians, a full circle, measures 2 pi radians. So another way we could put this is that we want to convert 270 degrees into radians by noticing that 2 pi radians is the same as 360 degrees. So this division here of 270 divided by 360 is pivotal. That's the ratio of the circle we're talking about. And then we want to think about that in terms of 2 pi radians per circle. So either way you do it here works. This is the kind of conventional unit conversion motif. So we'll do this. This is 2736 times 2 pi. 2736, that's just getting rid of both of the zeros there, times 2 pi. 36 and 2, this becomes 18. So we really have 27/18 pi's radians. If you converted this to a decimal or reduced it more, can I reduce it more? Oh, I can. So 9 goes into each of these. So this is really 3/2 pi radians, right? 9 times 3 is 27, 9 times 2 is 18. So we have 3 pi radians, 3/2 pi radians for the answer to number 27. And that's it. Number 25, extra credit. A 160-degree circular moat protected a castle. 160 is just less than 180 degrees, and this is a moat. All right. The inner border of the moat had a radius of 100 meters. The moat was 30 meters across, and it was 5 meters deep. How much water was needed to fill this moat in cubic feet? So I need to know, I look at this on the profile, there's a trough, I'm just assuming it's a rectangular moat, and it's 5 deep, and this is on a curvature, right? And so we need to know how much water would fill this entire moat all the way around that curve. Where the tangent lines can be drawn to the outer corners, a special point exists beyond the moat some distance, so out here, where the tangent lines can be drawn to the outer corners of the moat arc. So I can draw a tangent line like this, and a tangent line like this that touches just at that point. These two will eventually come together at some point out here. At what angle, at this special point out here, do those two tangent lines intersect? So we'll do that second. First, let's get this right here. So we have a 100 meter radius, and we have a 360th, new piece of paper here, 360th proportion of the entire circle, just 160 degrees of the full circle, of this radius 100 circle. So we're talking about the area of the 130 radius, which is pi times 130 squared, minus the, let's do this inside of the parenthesis, that's the area of the entire outer shape, circle, minus the inner, which is pi times 100 squared. So this together will give us the difference between the outer and the inner, or subtracting off the inner will give us just the moat portion. And the 160 by 160 360ths will give us just the moat, just the portion of the moat from here to here, not all the way around, since it's only that long. All right, so 130 squared pi minus 100 squared pi. Can't just subtract 130 from 100 here, unfortunately. So I have to actually do this. This one right here is not too hard. There we go. It's that many pi. This one is a little harder. I'll go ahead and do it over here just to be on the careful side. We've got 0, 9, 3, 0, 0. We've got 0, 3, and 1. 0, 0, 9, 6, 1, 6, 9, 0, 0. 9, 0, 0, And I feel like that suggests I made a mistake here. Oh no, that's right. Okay, so 16,900 pi minus 10,000 pi is going to give us minus 10. It's going to give us 6,900 pi inside our parentheses here. So we have 16/36 of 6,900 pi. So how do we do that? Well, let's go ahead and reduce this. It's 8/18 or 4/9, and that seems right. 4/9, 6,900 pi. 69 doesn't go into 9 nicely, so it looks like I have to do a little bit of extra work here. I don't think I'm going to gain anything by multiplying first. So this would be a good candidate for a calculator. I'm not going to do the arithmetic right here. I'm just going to call it this number of, what's our units? Meters. So this many meters squared. And we're going to have to actually multiply that by this depth, the depth of the moat, 5 meters, in order to get our volume. So our volume is going to be 5 times 4/9 times 6,900 pi meters cubed, because now we've got meters times meters squared, so the whole thing is going to be in meters cubed. Again, I don't think that this gains us much. This becomes 20/9. Again, this is just arithmetic that I'm not interested in doing right now, so perhaps I'll do this later and get you that number. But if you got that right, that's what your number will be there. Okay, the second half of the problem says, at what angle do these tangent lines intersect? And so we have very poorly drawn a 130 meter radius moat edge, and it's going just to 120 degrees, so that right there is 120 degrees. And we're talking about 2 tangent lines that come to a special point right here. What is the angle at this point right here? That's the question. All right, this one takes more intuition than anything. A tangent line means that these are 90-degree angles right here. So we have 120 degrees, 90 degrees, 90 degrees, and 4 angles. A 4-sided shape will always have a total of 360 degrees. So we need to add up to 360 degrees, given that we have 120 plus 2 90s, which are 180, plus this unknown alpha. So 120 and 180 are 300, and 360 minus 300 is going to give us alpha left over on this side and mere 60 left over on this side, and our angle there is going to be a 60-degree angle.